Hi class, this is part 3 of section 6.4. In this video, we will continue to graph logarithmic functions. In part 4 is where we solve logarithmic equations. The PowerPoint lecture questions are in part 4. Okay, so we're still in example 5 up to part C. Our function is f of x is equal to log of the quantity x plus 1 minus 3. Okay, so the domain, again, we get by looking at the function. So the input to the log must be positive. So x plus 1 must be greater than 0, which means x must be greater than negative 1. So we'll go from, negative 1 to infinity. To graph the function, let's first replace the f of x with a y. So I have y equals log of x plus 1 minus 3. So this is the first function we've seen where we have this, what would be a vertical shift to the graph, right? It would shift our graph down 3 units. Okay. In order to write the equation in terms of an exponential equation, I need to add the 3 to the other side. So we'll have y plus 3 is equal to log of x plus 1. Okay, so if you remember, when we have log with no base, it's the common log, which means it's base 10. So to write this exponentially, we have 10 raised to the y plus 3 power is equal to x plus 1. So to solve it for x, just subtract that 1 over. So 10 raised to the y plus 3 power minus 1 is equal to x. Okay, so this is what we'll use to find points that are on the graph of our log function. Okay, so even though you have the log button on your calculator, I don't want you just picking values for x and plugging them in because I want the ordered pairs that you're plotting to be ones that make sense. Okay, so for our y values, we need to notice that the first thing we're doing is we add 3. Okay, so let's pick our y values. That way we can kind of undo that adding 3. So normally I would just let y equal negative 1, 0, 1, and 2. Okay, but this isn't going to work because we would have, if y is 2, this would be 10 to the 5th power, which is a huge number. We certainly don't want that. Okay, so I'm going to erase these. So when I say we have to kind of be mindful of that plus 3, that means I'm going to subtract 3 from those numbers. So we're really going to start with negative 4. That way my exponent is going to be 10 to the negative 1st power. Okay, and then I also want to use negative 3, negative 2, and negative 1. Okay, that way when I plug it in, I really do get 10 to the negative 1st power, 10 to the 0 power, 10 to the 1st power. Okay, which is what I want for those exponents. Okay, so 10 raised to the negative 4 plus 3, and then we subtract 1. So again, this is 10 to the negative 1st power minus 1. 10 to the negative 1st is 1/10. Minus 1, this is negative 9/10. Next, plug in a negative 3. So negative 3 plus 3 is going to be 0. So this is really 10 to the 0 power. And then we take 1 away. So 10 to the 0 power is 1 minus 1. So we're at 0. Next, we're going to plug in a negative 2. So this gives us 10 to the 1st power, which is 10 minus 1, so 9. And then if my y value is negative 1, this is really 10 squared minus 1. So 100 squared minus 1 or 99, right? So that's not going to be a good point. But sometimes it works out, but the base was too big. The base is 10. If the base was only 2 or 3, then that one would have been probably feasible. Okay, but these are the 3 values that we have that we'll plot on our graph. All right, so let's put in our vertical asymptote. So the line x equals negative 1 is a vertical asymptote. We get that by looking at the domain of the function. So the vertical asymptote is whatever number you're approaching. So we're allowed to approach negative 1 but never get there. So x equals negative 1 is our vertical asymptote. Okay, I'll start with 0, negative 3. 9, negative 2, so 9's actually, I'm going to switch to green. 9 is a bit off the graph, so 9, negative 2 would be right there. And then 9, negative 9 tenths, negative 4, so a number just to the right of negative 1. Okay, so these are my 3 points, right? Kind of the best we could have done. So that's why it's good to rewrite the equation exponentially, because it's sometimes getting these coordinates can be tricky. Okay, and I want them to be, you know, nice whole numbers or a fraction that makes sense. So if you're talking about base 10, then having the fraction negative 9 tenths makes sense. Okay, so here's the graph of our function. Things that I'm looking for on the graph are that you have, you're going through the points that you're supposed to go through. So they're either labeled on the graph or over here on the table. That vertical asymptote is labeled, it's marked on the graph, it should be a dashed line, and it's clear that your graph is getting closer and closer to that horizontal asymptote with, sorry, that vertical asymptote without crossing it. Okay. So there are our coordinates, and let's move on to find the inverse. So again, we've done the work to find the inverse of the function, but if you're unsure, remember just replace that f of x with y, switch x and y, so this in here is a y plus 1. Okay, one thing we have to remember is that the 3 needs to be added over first. Otherwise, we can't write it as a exponential equation. When no base is written, it's the common log, meaning it's base 10. Rewrite this exponentially, so the base is 10, the exponent is x plus 3, and this is equal to y plus 1. Okay, subtract the 1 over, and that's it. So f inverse of x is 10 raised to the x plus 3 power minus 1. So that is our inverse function. Okay, good. Exponential growth, since the base is 10, so this is going to be pretty rapid growth because 10 is one of the larger bases that we're going to be looking at. You could graph it using transformation, right? We've moved it down 1 unit. Adding 3 moves it to the left 3. Okay, same thing here. Once you get used to the log functions, thinking about transformation will help you. Okay, also it can confirm that the domain makes sense, where that vertical asymptote should make sense when you think about transformations. Okay, so there's our logarithmic function again. And now here's our exponential function on the same graph. Okay, so a couple things. The log function, I have it here in black, it's getting closer and closer to the black vertical asymptote. It grows off and goes off to infinity. So it does eventually pass that horizontal, right? It doesn't look like that. But my point was that it eventually passes this horizontal asymptote, okay? Our exponential growth function only has a horizontal asymptote, okay? It goes off to infinity, but remember the domain is all real numbers, so it'll eventually cross that vertical asymptote and keep going. Okay, so even though the graph has 2 vertical asymptotes, try to keep straight which one is for which graph. Okay, part D, we have the function g of x is equal to e to the x plus 1 minus 2. I think this is in this section, just to make sure that you guys are paying attention. So this is back to an exponential function. It looks like exponential growth because e is between 2 and 3, right? So a number bigger than 1, so we get exponential growth. Thinking about transformation, the graph will move, let's see, plus 1 will move it to the left 1 unit, and then minus 2 will move it down 2. So when it shifts down 2 units, the horizontal asymptote will move along with it. So the horizontal asymptote for our graph will be y equals negative 2. It's an exponential function, so the domain is all real numbers. Okay, so when I pick values, I'm back to picking x values, again, because it's an exponential function, not a logarithmic function. I want to be careful since the first thing I do with my x value is add 1. So I'm going to start with negative 2 and then use negative 1 and 0. instead of using -1, 0, and 1 like I normally would. Okay, let's plug in that -2. So we would have e to the negative first power minus 2. You could leave it like that or write this as 1 over e minus 2. You can find a decimal approximation with your calculator as well. If the exponent is, if the x value is -1, I'm going to get e to the 0 power minus 2. So e to the 0 power is 1 minus 2. So we're at -1. And then finally, if x is 0, we'll have e to the first power minus 2. So remember, e is approximately 2.7. So when we subtract 2, we're at about 0.7. Okay, so on the graph, I'll start by drawing in that horizontal asymptote. So this should be a dashed line on your graph. I'll start with -1, -1. Let's see, 0 is approximately at 0.7, so we'll put that right there. And then when the x value is -2, the y value has to be just a little bit above that horizontal asymptote. Okay, so again, you can kind of estimate where that point's going to be, even if you didn't get a decimal approximation for 1 over e minus 2. Okay, so there's a graph of our function g. It's our exponential, it's an example of exponential growth. Okay, so now to find the inverse. So we're starting with an exponential function, so its inverse will be a logarithmic function. Okay, so let's replace that g of x with a y. So I have y equals e to the x plus 1 minus 2. Switch x and y. X equals e to the y plus 1 minus 2. Let's add the 2 over. So I need to write this as x plus 2 equals e raised to the y plus 1 power. So we have to add that 2 over first. And now at this point, we are ready to switch our exponential equation to a logarithmic equation. All right, so the base is e. So I'm going to do this in 2 steps. That means this is going to be log base e of x plus 2. And this will equal y plus 1. Okay, we don't normally see log base e. So hopefully you remember that log base e is equivalent to our natural log function. So I'll write this as ln for natural log. ln of x plus 2, let's subtract that 1 over, and this is equal to y. So this is our inverse function. This is g inverse. Okay, logarithmic functions do have a restriction to the domain, right? So you can only plug in positive values. So you should be able to see that the domain will be from -2 to infinity. Parenthesis on the -2 because we can't get there. So I'm looking right here, this x plus 2, this is what needs to be positive. So that tells me that I'm going to have a vertical asymptote on the graph at the line x equals -2. All right, this makes sense because my exponential growth function had a horizontal asymptote at y equals -2. Okay, so those are going to switch as well. The point -1, -1 is going to be on both graphs, since if you just switch it, it stays the same. Let's see, 0.7 is going to become 0.70, and then this value 1 over e minus 2 is approximately -1.6. Okay, so when that switches, we are going to have -1.6, -2. So about right there. Okay, so these are 3 points on my logarithmic function. Again, you have to have an idea of what it looks like. So I'm going to start off here coming from that horizontal asymptote. Okay, and then it grows very slowly, right? As opposed to that exponential function, which shoots up. Okay. Good. And I said this before, but the logarithmic function does grow very quickly when you're near that horizontal asymptote. But once you get further to the right, that's when the growth is pretty slow. Okay, let's see, the domain I have for my inverse function, the range will be all real numbers. So the domain for my original function g was all real numbers. So the range will be -2 to infinity. Okay, so there they are, both graphed on Desmos. You can see that if you could fold it along the line y equals x, those two would match up. Okay, good. So I hope this was helpful. I know it's a lot. In the next video, we're going to talk about solving equations, and then also that's where you'll have your PowerPoint lecture questions. Okay, thank you for listening.